Thank you.
Welcome everybody to our colloquium this week. Pleasure to introduce Ilias Kotsireas. Tell us about 20 years, more than 20 years of Legendre.
Thank you, Taylor, and thank you to the department, Graham and Taylor, for inviting me. It's nice to be here in this very building where I was a postdoctoral fellow 23 years ago, in 2000, at the ORCA, the Ontario Research Center for Computer Algebra, and David is an Orcadian from that time, and still is. I moved on to other areas of research since I was a postdoc, and basically I started working in design theory and doing computational work in that area. And one of the objects in design theory that I want to discuss today is this so-called Legendre pairs. They were introduced in 2001, so it's been 20 plus years of various developments in this area. And I want to demonstrate why these objects are important. And as you have seen in the abstract, they are important because they are related with a conjecture, a famous conjecture in discrete mathematics called the Hadamard conjecture that I will discuss in the second part of the talk. So there are very few mathematical ingredients, if you like, that we need in order to define Legendre pairs. And the first one is this one here, the periodic or the correlation function, abbreviated as PAF. What it is that we start with a discrete sequence of finite length, this length n, and we define the PAF, or the periodic or the correlation function coefficients, by this formula, which essentially says that you take your sequence, you shift it in a cyclic manner by S, and then you take the inner product of the original sequence and the shifted sequence, and this is the value. This is a number called the PAS, the periodic or the correlation function at S. And there is this nice symmetry property that tells us that these coefficients are symmetric with respect to, let's say, the middle of the sequence. So you only need to know about half of them, not all of them, not up to n, but up to n over 2. There is another property that if you add up all these coefficients together, you get twice the second elementary symmetric function in your original variable. So this is a nice connection with another object which is very well studied in combinatorics. And finally, if you have a circulant matrix whose first row is equal to this sequence, then this PAI is the inner product of the first row of the circulant and the I plus 1 row of the circulant. So a circulant matrix is like a Toeplitz, very special case of Toeplitz matrix, even simpler than Toeplitz. It's defined by the first row, and every other row is a right cyclic shift of the previous row. So this is the first ingredient. The second ingredient is even more well-known, I would say. It's the discrete Fourier transform. So this is the usual definition of the discrete Fourier transform. It's just a whole bunch of these n complex numbers defined like this, where this omega is a primitive nth root of unity. So there is nothing complicated about this definition. It's classical definition. And what we do with it is that we take, for every one of these elements of the DFT, we take the real part squared and the imaginary part squared, and we call this, for historical reasons, power spectral density of the sequence associated with this index K. And these historical reasons that we call this PSD have to do with engineering applications that I'm not going to go into. So we have these two concepts, and with this we can already give the definition of this combinatorial object called Legendre pairs, and we will see in a minute why they bear the name of Legendre. So if n is odd, n has to be odd, and we have two sequences A and B with n elements each one, and the elements are plus and minus 1, then they form a Legendre pair if, when you compute the paths of A and of B and you sum them up for every S, then you get the constant -2. And this is done for every s from 1 up to n-1/2. Remember, we only need to know half of the path values. The other half are equal to the first half. So this is a very simple definition, right? It just tells you you compute the path coefficients, and at every s, they have to sum to the same constant, and that constant is -2. Typically, we use this normalization that the sum of the elements of A and the sum of the elements of B have to be equal to 1. And this is without loss of generality due to symmetries. And this gives us an upper bound on the potential numbers of A and B sequences that we can use to make these Legendre pairs. Yes, please. Yes, there is in the first few slides, in the next few. Yeah, okay, sounds good. We will, yes, it is, it is. So we will elucidate both of these points soon. Thank you. In Signal, I know of applications in telecommunications and coding theory and the rest. I don't know about Signal, but I'm not an expert in Signal. So this upper bound is this central binomial coefficient, n +1/2. And there is another property that they satisfy, which is a consequence of this definition, that the sum of the PSDs, so these values computed via the DFT, they also sum to a constant for every s, although this constant now depends on n, so it's 2n + 2. This constant doesn't depend on n, this one does. So summary, if you like, Legendre pairs characterized by the constancy of these two invariants, the path, the periodic autocorrelation function with constant -2, and the PSD with constant 2n + 2. So, because they don't exist for even n. Yeah, there is some Diophantine equation obstruction that forbids existence for even n. But if you change the alphabet, if you allow, so this is second root of unity, if you expand the alphabet to fourth roots of unity, then they exist for even and odd together. But in this case, in the original case, that was as was defined by this Australian cryptographer and design theorist, Seabury, from 2001, in her case, it's just odd. So examples, it's about time. N = 11. A and B are these 11 plus and minuses for A and for B. They sum to 1 for A and for B. The PSD constant is 2 times 11 + 2, 24. The first 5 path values are all -1 for A, for B -1. If you add them up vertically, you get the -2. Simple enough. Now, n = 13. This is a Legendre pair of order 13, 13 plus and minus 1s for A and for B. The first 6 path values, so 13 - 1/2, right? They are 1, 1, and so on. For B, -3, -3. If you add them up vertically, you always get -2. And you probably notice that while in this case, the -2 is easier to obtain, you just add up 2 -1s. Here you don't have this property. And this is not accidental, of course, as we will see in a minute. This is a bigger example, 37 plus and minus 1s for A and for B. The first 18 path values, again, -3, 1, If you add them up, you get 18 times the -2 constant. So it is a Legendre pair. But now I also want to demonstrate the PSD invariant. For the PSD invariant, you compute for S = 1, 2, up to 18. This is the PSD of A at 1. This is the PSD of B at 1. The sum is 76, equal to the PSD constant, the 2 times 37 plus 2. Okay? And this happens all the way down up to 18. And you can also notice here, if you look at these values, that in fact, there are only two different values, right? The 25.8 and the 50.16 and so on. And that is also not accidental, but the sum is always equal to 76 in exact arithmetic, right? Although these are floating point values, the sum is equal to 76 as an integer in exact arithmetic. So that means that in algorithms, in algorithmic schemes, to look for Legendre pairs, you have to pay attention to these properties. Otherwise, your code will be, correct.
Those turn out as
Yeah.
decimal representation, something rational, or are they just?
No, these are not rational. These are floating point numbers, because the DFT is something with a lot of cosines, a lot of sines in there. So in very special cases, you will get rational numbers. Very special cases. In the general case, let's say for primes 37 or 59, or then it will not be. It is an exact number, but algebraic, if you like. It's not an integer. In some cases, it is. So, but again, very special cases. This is another example for n equals 55. Again, the 27 path values here they are. Now you have bigger numbers, -9, 7, and so on. But again, the sum vertically is always equal to -2. So it's a pretty stringent, a severely constrained problem, if you like, from a number of quadratic equations. The path is a quadratic function. So why are they called Legendre pairs? Well, there is this nice, beautiful construction, which is the following. I will illustrate it in Maple. This is not a proof, obviously, but you can write down the proof. It's an easy exercise in autocorrelations. For every odd prime P, there is a Legendre pair of order P via the Legendre symbol from number theory, the usual Legendre symbol that indicates whether something is quadratic residue or not, right? So in Maple, we load the number theory package. We put together the sequence, seq of Legendre symbols from I, P, from I from 1 to P minus 1. P is our odd prime. We prepend 1 in this sequence. Then we take the negation of this sequence and we prepend 1. And this is your A and B. This is a Legendre pair of length P for every odd prime. So this simple construction tells us how to make these Legendre pairs for every odd prime, right? So there's nothing else to do there. By the way, there is an interesting behavior according to the parity of the prime modulo 4. If P is 3 modulo 4, then all the path values are equal to -1. All the PSD values are equal to P plus 1. And so when you add them up, you get the path constant -2 and the PSD constant 2P plus 2, as expected. But when your prime is 1 mod 4, then all of the path values belong to 1 and -3. There are only 2 different PSD values, and for a long time I had no idea why this was the case until I bumped into this guy here, Arne Winterhoff, who is a number theorist at the Austrian Academy of Sciences, and he said, well, of course there are 2 values. It's just the Gauss sum. Everybody who knows the definition of the Gauss sum realizes that it has to appear in this context, because the definition of the Gauss sum contains Legendre pairs, right? So the Legendre symbol, I'm sorry. So again, although we have this complication with the Gauss sum, again, when we sum them up, we get the constant -2 for the paths and the PSD constant 2P plus 2 for the PSD values. So irrespective of whether or not it's 3 or 1 mod 4, we get what we need, and we have a Legendre pair. Now there is another construction called the twin primes construction. And that construction goes like this. For every twin prime pair P and P plus 2, okay, there is a Legendre pair of this order, P times P plus 2. How does this construction work? Well, first of all, you have to find G to be a common primitive root of P and P plus 2. So the generator of the cyclic group kind of thing, right? But no one can tell you for sure that there is a common primitive root. So P and P plus 2 may have several primitive roots, but we need one which is common for P and P plus 2. And this is another sort of open conjecture. But if you believe it, so you can write some Maple code. That's what I did, and I couldn't find the counterexample. Then I asked, famous number theorists around the world, Igor Sparlinsky and others in South Africa and in Canada and in India and here, there. And they all said the same thing. This is an open conjecture. So if you believe it, then there is this G, then you set up these parameters, then the positions of the minus ones in your sequence are encoded by these indices here. And lo and behold, you get a Legendre pair of order P times P plus 2. It's essentially one sequence that you use it twice. It has the property that the path values are equal to all to minus 1. So when you add up 2 copies, you get the minus 2. Okay? But the caveat of this construction is that first it relies on the twin prime conjecture, which is one of the most famous open conjectures in number theory. And if this is proved, then you get an infinite class of Legendre pairs and the associated Hadamard matrices that I will come to in a minute. I don't know. I'm not sure. There may be, but I'm not sure. There are many Lambert W experts here. I'm not one of them. So this is the second construction I wanted to mention, and how all of this is related to the Hadamard conjecture that I will come back to in a minute, which is open since 1893, if you like, and sort of Sylvester in the implicit in the work of Sylvester, that there is a Hadamard matrix of order 4n for every n from 1, 2, for every n, 1, 2, and so on. These are the smallest open cases, 6, 6, 8, 7, 16, and 8, 92, less than 1,000. And this is some approximate timeline of state-of-the-art work in the Hadamard conjecture. So from 1985, it took another 20 years to get from this 268, the smallest unknown order, to this 428. And then our own contribution was here in 2014. We found the Hadamard matrix of order 1004. And Shalom Eliyahu in France has a very nice website here on the Encyclopedia of Mathematics Encyclopedia of the CNRS. You can read up more on the Hadamard conjecture. I will come back to it in a minute. So what is the connection of these Legendre pairs and the Hadamard matrices concept? Well, here it is. If you start with a Legendre pair A, comma B, then you take the circulant matrix CA and CB, you make 2 circulant matrices, and you stick them into this template array. So this is circulant A, circulant B transpose, and minus CA transpose. And then you border this template over here. So this is 2P by 2N by 2N, this submatrix. You border it by 2 rows and 2 columns with this pattern of plus and minus ones. Why do you do that? Because you need to get the orthogonality condition of Hadamard matrices. And it turns out that then this matrix, which is of order 2n plus 2, is a Hadamard matrix. And that means if you take the product with its transpose, then you will find 2n plus 2 times the unit matrix. So if you have an LP P, a Legendre pair of order P, then you construct Hadamard matrices of order 2P plus 2 for every prime P automatically. From the twin primes construction, from this Legendre pair, you make up this Hadamard matrix. And in general, if you had a Legendre pair for every odd n, then you could realize any Hadamard matrix like this one here. So the Legendre pairs, in other words, give you a structured version of the Hadamard conjecture. The Hadamard conjecture is too general. It says there is a Hadamard matrix, period. But it doesn't say what kind of Hadamard matrix it is. There are hundreds, literally hundreds of constructions for Hadamard matrices. And most of them have some deficiency that they don't work for certain parameter values. This construction here is more promising in my opinion, and that has been conjectured by other people implicitly or explicitly, including myself. So the conjecture is that these Legendre pairs are enough to construct every Hadamard matrix that you need. And the reason is, of course, that when n is odd, then 2n plus 2 ranges over the entire multiples of 4. Okay? So this is why Legendre pairs are interesting. And again, we know what to do when the order is a prime. We know what to do when the order is a product of twin primes, although this is a very sparse sequence, the product of twin primes. Yes, please. Yes. These Hadamard matrices here are of a very special form. They come from this Legendre pair, right? But there are other Hadamard matrices that have nothing to do with Legendre pairs. So there are, as I was saying, hundreds literally of constructions. There is no, I think, expert who knows all of them. You know, very few people know maybe half of them. There are literally hundreds of constructions, but none of them works for every multiple of 4. That's the only problem with all of them, except possibly this one here. So in other words, there is no counterexample for this construction yet. There is no Hadamard matrix that someone can say definitively it cannot exist in terms of this construction. No counterexample. So for prime numbers, we know what to do. For products of twin primes, we know what to do. But in general, we have no idea how to approach this problem. But in 2015, we wrote this paper with Djokovic, who is a mathematician at the University of Waterloo, whose main work was in Lie groups and Lie algebras and all the rest. But he also did a lot of work in this kind of combinatorics. So we put together this concept of compression, and it's meant to remedy the problem that we don't know what to how to compute Legendre pairs when the order is a composite number. So we take the order V of a sequence, any sequence, doesn't have to be a Legendre pair, for any sequence of order V where V is dm, and this is a non-trivial factorization. We define these sequences of subsums. So these subsums AJD, where we take elements from the original sequence which are situated D apart. So AJ plus D, etc., up to this one here. We do that for J from 0 to D minus 1, and we assemble all these D elements together in a sequence AD, A upper script D, of length D, and we call it the M compression of A. So why is this useful? It's useful because if now we have a Legendre pair of order V, where V is a composite number, A and B are the sequences, then we can compress these two sequences by the same M, and we get these two sequences AD and BD of the same length D. The alphabet is from minus M up to plus M, obviously. We just take sums of M plus and minus ones, so that's the new alphabet. And now the sum of the puffs is also constant. but it's not -2, it's -2 times m, where m is this compression factor, and the sum of the PSDs remains the same as the original PSD constant, so 2V plus 2. Therefore, m compression has the effect that scales linearly the path, -2 times m, and the PSD remains invariant. So that is what we came up with. And now how do we use it? Well, first here's an example for LP15. 15 is composite. We can do 3 compression and 5 compression, and these are the sequences. This is a sequence of length 5. The first element is a triplet, a sum of 3 elements. The indices differ by 5, so 0 plus 5, 5, 5 plus 5, 10, and so on. You see the logic, it's a pretty simple construction. And for 5 compression, we have 3 elements in every sequence, and now it's a sum of 5 elements that differ by 3. And now what is the point of all this compression business? What do we gain in terms of computation? Well, let's take this example, 133, which is a composite number, 7 times 19. Suppose that we have a Legendre pair, and we do. Then we can compute its 19 compression, and it's this sequence, 2 sequences of length 7, very small sequences, very mild growth in the elements here, right? 5 7s, 1 7, a few 5s, 1 3s, -3s. So these 2 sequences, if you think about it, encode a Legendre pair of order 133, so with total 266 elements, right? This is a very small encoding of this object. And if we compute the paths, they sum to -38, -2 times 19. And if we compute the PSDs, they sum to this, as expected. Now, the issue is, can we do the opposite? If someone gives you this A7 and B7, how do you recover your Legendre pair? And we call this decompression. And decompression is computationally expensive, but it's a lot better than working with 133 variables twice, right? It's a lot better to work with 7 and 7. So the problem, the caveat with compression is that it's not an one-to-one mapping or an onto mapping, depends how you define it. In other words, if someone gives you another pair, A7 tilde and B7 tilde, with the path to sum to -38 and the PSD to sum to 268, it is not guaranteed that the compression will give you a Legendre pair of 133. So this compression has the effect that encodes a Legendre pair in a pair of very small sequences. But the caveat is that if you try to do this the other way around, so this is how we found, in fact, this 133 by finding pairs of this kind and then try to decompress them. So we have to look at a few thousands of these pairs, and one of them worked and gave this LP 133. Okay, yeah. This is the decompression is done with a C program, right? So you run it, and if you get the result, that means that it can be decompressed. There is no theoretical guarantee. That would be, a gift from above, right? To have a theoretical guarantee to know which ones of these tilde pairs will give us a Legendre pair and which one will not. That would be extremely useful, but we don't have that. So for now, it's ad hoc. Yeah. Yes, you will. Yes, you will. You will find the same Legendre pair or something which is equivalent by symmetry. The class of symmetry defined by a Legendre pair contains n squared elements. So every cyclic shift of a Legendre pair in A or in B gives you another Legendre pair. So when you decompress, you will find one of these in this symmetry class, one of these Legendre pairs. Thank you for the questions.
before.
There is no,
We did this before.
not that I know of. Okay, then the compression was in 2015. Then in 2021, that was one of the COVID papers, as I like to call it, when everybody was on Zoom doing something. This is what we were doing. Jonathan Turner here, the first author, did a PhD thesis on Legendre pairs. In fact, an amazing piece of work with a lot of untapped theorems in there and techniques. And he put together he pioneered, if you like, the idea of simultaneous decompressions, which means if your Legendre pair, let's say it's order 77, 7 times 11, he said we don't need to look at 7 compressions or 11 compressions alone. We can look at 7 and 11 compressions together. So it's a PhD thesis, right? So I'm not going to go into the details, but anyway, using his ideas, we managed to solve this LP77, which was an open problem since 2001, pretty much. And we found it. We sent it to a reputable journal called DCC, Designs, Code, and Cryptography. The editor was very surprised and accepted it in 15 days, which is very, very unusual for any journal. The point of working with this computational, if you like, approach is that you can unravel some new ideas, if you like, or start looking for properties that you've never seen before. So with the 77, when we computed it, then we took the 11 compression, obviously, and the 7. And here is the 11 compression. It's these two sequences. So we know that they have to sum to, the paths have to sum to minus 22, minus 2 times 11. But how does this minus 22 materialize? And we've seen that it materializes like this: 3 minus 21s and 3 minus 1s. When you add them up vertically, you get the minus 22. So obviously, this is not random. There is a lot of structure here. And this structure tells us that if your compressed sequences have this path constancy property, so if they have constant path, like this one here and this one here, then you have better chances to actually get a decompression. Okay. So, and in another paper, again in 2021, another COVID paper with Christoph Kutzan here, German mathematician who works in Linz in Austria and well known in the computer algebra and the combinatorics circles. We sort of elaborated when this constancy property might hold for an arbitrary divisor M of L, the order of the Legendre pair. So if the M compression of AB that we call calligraphic A, calligraphic B, is made up from 2 constant path sequences, so the paths are equal, the paths of A and the paths of B are also equal, then the PSD values at integer multiples of M of A and B are integers. They are not floating point numbers. This is another surprising property, but it is what it is. They're integers, exact integers, and they have the implicit evaluations. Here they are. The PSD of A at M comma S for every S up to here is the sum of the squares of A. So this is the second power sum function minus the first path value, which is equal to all the other ones anyway, and the same for B. So we have this elaborated, this nice property, and we also did something else in that paper. We were able to elaborate the complete spectrum of the L over third value of the DFT and the PSD value for a Legendre pair when L is 0 modulo 3. So when the Legendre pair order is divisible by 3, then we're able to say, for instance, this is a sample result. If L is 117, 3 times 39, then we can prove that the PSD A at 39 and the PSD B at 39, the spectrum of these values is a very, very small set, just three different possibilities only, right? Although you have this big length over here, the PSD 39 must belong to these three pairs of values. And this helps us because we can parallelize search algorithms. We run one search for this one, and one for this one. So we parallelize the search and get to find Legendre pairs faster. So the state-of-the-art list of these 12 integers in the range less than 200, for which the question of existence of Legendre pairs remains unresolved, is this one here. In the meantime, we got rid of 85 and 87. So we found those. And now the smallest one is 115. So this is the, if you like, the computational state of the art in this problem. And this is another work which is ongoing. Because we have this multiples of 5 over here, 1, 2, 3, 4, 5 multiples of 5. We focused our energies on Legendre pairs whose length is 0 mod 5 in general, and we have some nice conjectures over here. I will not go into the details. This paper is on the archive. You can find it, and we had a lot of feedback with another student of Jonathan, and also a statistician from Virginia Tech. Anyways, this is work to be done. So may I switch to the second PDF, the second PDF file? Yeah, sorry to. Yeah. No, not for Legendre pairs. No, nothing. So the conjecture is that they exist for every n, right? So there is no obstruction to this conjecture, theoretical or computational. It's just a matter of time. It could be around, yeah, I don't know. It could be, yes. Yeah, of course.
That the not plus and minus one is here, like the type of orthogonal matrices, yeah, it's asking the algebraic equations.
You mean expanding the alphabet from plus and minus 1 to
Complex numbers, for example.
yeah, so we look with Arne Winterhoff. We have a paper where the alphabet is plus minus 1, plus minus I, so fourth roots of unity. Because these complex Legendre pairs give complex Hadamard matrices and so on. But they also give real Hadamard, right? So yes. This is a bit more information on the Hadamard conjecture. If you like, in the second part of my talk, I want to mention that Hadamard matrices are matrices with plus and minus 1 element, so that the product with a transpose is n times in. So they're kind of orthogonal matrices. If you scale them by 1 over square root of n, here if you take this n and put it here as 1 over square root of n, then this scaled version is an orthogonal matrix. There are the trivial cases n equals 1 and 2. There is a well-known necessary condition that n must be a multiple of 4. And the sufficiency of this condition is the celebrated Hadamard conjecture, which is open since 1893. We talked about the remaining things, but I didn't talk about this. So the two of my favorite sources, for Hadamard matrices literature, is this book here by Kathy Horadam, who is a retired combinatorialist from RMIT in Melbourne. And the handbook of combinatorial designs is an amazing resource. There is a chapter in there dedicated exclusively to Hadamard matrices. And there are some results here about 20 years ago from Lam, and Tontsev, bounds on the number of possible Hadamard matrices. And from those papers, we know that the number of inequivalent Hadamard matrices of order 40, for instance, is at least this times 10 to the 11. So there is an ample supply of Hadamard matrices, right? It's not that they are rare. They are not rare. They exist in great abundance, if you like. So this is sort of in support of this conjecture, right? They don't die out, if you like, when the order grows. Well, Hadamard was concerned with the maximum determinant problem. So he was looking at square matrices with plus and minus 1 elements, and he wanted to find the maximum determinant. And the maximum determinant is the famous Hadamard bound, n power n over 2 in absolute value, right? And these matrices satisfy the Hadamard bound. They're the extrema, the global minimum, the global maxima, if you like, of this function over the entire space of plus and minus 1 matrices. That's how they arise. And also Sylvester, but I don't know Sylvester's work that much. So I mentioned there are hundreds of constructions for Hadamard matrices, and these are some of them. The Kronecker product. So if you have Hadamard matrix of order n and order m, then you can make a Hadamard matrix of order the product. Then you have this Gruner's theorem with the twin primes that we mentioned already. Then we have this Paley construction, quadratic residues of primes 3 mod 4. If you take this sequence here, then you can make a Hadamard matrix for every prime 3 mod 4. Then you have the Williamson method from 1944. Williamson said the following: if I have this array, A, B, C, D, and minus A, this template array, and if A, B, C, D are symmetric circulant matrices of odd order n satisfying this equation here, the sum of the squares is 4n times in, then this is a Hadamard matrix. And for some time, it was thought that this construction will solve the Hadamard conjecture. But unfortunately, it was found that this construction fails for n equals 35. When this n is 35, then this construction fails. So this is not a good candidate to solve the Hadamard conjecture. And you can go to this NASA blog here. It's a delightful story of how these mathematicians, Baumert, Golomb, and Marshall Hall, found this HM92 for n equals 23 with this array. And they were so delighted because they could use it in some space exploration mission at JPL. Anyway, there's many other things. So there are problems with this construction. As I mentioned, Djokovic found that it fails for n equals 35. And then it also fails for 47, 53, 59. So this construction dies out, right? In small values, less than 100, this construction doesn't work. So there are literally hundreds of constructions, and again, they have this problem. They either produce a sparse set of orders, like the twin primes, or they fail for specific parameter values. And you can't rely on these constructions. Even if you combine them together, it's not enough to prove the full strength of the Hadamard conjecture. And well, this is what I was telling you already. These two circulant core construction that we put together, if you like, in this paper in the European Journal of Combinatorics, and later on in these proceedings edited by Jonathan Borwein and Sparlinski and Zudilin. We give some more details on this construction. And we went through all of that. So what I really want to say in the last 15 minutes or so is to show you some exhaustive searches. So we did some exhaustive searches for Hadamard matrices that come from Legendre pairs exclusively. And here's the result. So this is L, the order of the Legendre pair. It must be odd, 3, 5, 7. We did it up to 31. This is the order of the Hadamard matrix. And this is the total number of Hadamard matrices that we obtain. And you see that there is a nice steady growth in these numbers, right? I was giving this talk online, and Neil Sloan was in the audience. And of course, he said, but why this is not in the encyclopedia yet? You should have, and it's my mistake. But the reason I didn't put it is that I wanted an independent confirmation. Because when you write a computer program, you can make a mistake. It's only natural to assume that these numbers are an artifact of my program. And I want to avoid that before getting to the encyclopedia. So for that reason, I looked at these two papers. So believe it or not, there are two exact formulas, not one, two exact formulas that give the number of Hadamard matrices for every n, which is a multiple of 4. The problem is no one knows how to prove if this number is always non-zero, right? So the first formula is in this paper here by Salome Eliahu, Enumerative Combinatorics and Coding Theory. It's in this Swiss journal, Enseignement Mathématique, 1994. And the other one is by Warwick Deloney and Daniel Levine. Warwick, unfortunately, passed away 15 years ago, but Daniel Levine is alive and well, and so is Eliahu. So Fourier Analytic Approach to Counting Partial Hadamard Matrices, Cryptography Communications, 2010. The Eliahu formula uses coding theory. The Deloney-Levine formula uses multidimensional integrals and residues with lattice walks. And both formulas contain a certain amount of technicalities that you have to absorb. And a question I always had and still have is why, and to me it's far from evident, why these formulas must agree for every n which is a multiple of 4. They must give the same number, no matter what, right? And I haven't been able to do that even for n equals 0 mod 4. I mean, for n equals 4, not for every. Not even for n equals 4, I'm not able to prove that, yes, they coincide. So Eliahu theory, my time is, I think I have 10 minutes, right? So I will try to.
You said there are two. So it's just an experimental fact that the two of them are equal?
Well, it's not experimental. They must be equal. They count the same thing. They count the number of Hadamard matrices of order n. Assuming they are correct, I assume they are. It's refereed papers, right? So if someone finds a discrepancy, then one of them is incorrect, right? But I don't expect it's incorrect. I believe they are correct. But I would like to, to be able to say, even for n equals 4, that they agree, that they give the same number, let's say 256 or something, some number. But it has to be the same number. They can be, but it's above my pay grade, let's say, or my skills, if you like. That's what I'm saying. I think I can do the first one, but not the second one, the multidimensional lattice walk and I got stuck in there. So I focused my energy on this first paper. It's an amazing paper, and that method, in fact, that he proposes in there, you can call it a theory. It works in several other contexts. And what it is the following. It exposes a fundamental link between the number of solutions of polynomial equations. Ta-da! Orca strikes again. Okay? Polynomial equations in binary variables with positive integer coefficients and certain associated binary linear codes and their weight enumerators, which are studied in coding theory. So here's some technicalities. If f is a polynomial of n binary variables with non-negative integer coefficients, then the enumeration of the values assumed by f on this Boolean cube, so the sequence is plus minus 1 length n sequences, is equivalent to the enumeration of the weights in an associated binary linear code LF. That's what this paper is doing. So this correspondence, in conjunction with the Mach-Williams identity, is used to enumerate Hadamard matrices of fixed order. And that's how this formula occurs in his paper. So is there a sequence of length n with plus minus 1 so that Fp is equal to 0? A binary 0, in other words. And how many? So we want to count how many binary zeros does this F admit. And the first thing that you do is that you encode all this information into this value enumerator of F, this Laurent polynomial in t and t minus 1, which is the sum of t to the Fp, where p ranges over this, the Boolean cube. So all these 2 to the n sequences of plus and minus 1s. And the coefficient of t to the u in this value numerator is the number of binary points p such that Fp is equal to u for every u in Z. And of course, we can set u equals 0 if we want to count binary zeros. So now how is this code constructed? First of all, we can consider only square free monomials. And the reason is that if you look at this expression, for instance, x squared y minus y, this is always 0, no matter what x and y are, if they are plus and minus 1, because this x squared is equal to 1. So this is 0. Therefore, you decompose F as a sum of monomials, which are square free monomials. And then you make this n times capital N matrix, phi, defined like this. Phi ij is 1 if xi divides one of the monomials uj and 0 otherwise. So it's some sort of indicator function like definition, right? And then you take the binary linear code generated by the n rows of this matrix. The dual code, LF dual, admits this phi as a parity check matrix. If you don't remember this coding theory, I don't remember it either. Anyway, it's a known concept in coding theory. And I will skip some technicalities in the interest of time. So the theorem is the following. F minus 1 of u, the cardinality of this F minus 1 of u, so the inverse fiber of u, if you like, is 2 to the n minus the dimension of the code times the coefficient of xy in this power in the weight enumerator of this code. And we use the bivariate weight enumerator. Okay? So there are many combinatorial objects, not all of them, but many that can be defined in this context, plus and minus 1 sequences of constant autocorrelation. You can think of them as a system of polynomial equations with positive coefficients. So they sort of render in Eliyahu's formalism. And we can do this Eliyahu theory counting for Hadamard matrices that come from Legendre pairs. And this is an example for L equals 3. There is only one equation. You expand it out and you end up with this after you simplify the square, the monomial, the squares, and so on, right? Square free monomials, you keep square free monomials. So capital N is 32, and this is your matrix phi, 6 rows, 32 columns. And now you can compute its weight enumerator. Here it is. You can do it in Magma. It comes out like this. So the dimension of the binary linear code can also be computed in Magma. It's equal to 4. Therefore, you use this formula to compute F minus 1, 0, the number of binary zeros of this, this function here, which defines the Hadamard matrix, and you get 36. So this equation has 36 solutions, and this is exactly the number that we found in our exhaustive search enumeration. So we did the same for the remaining dimensions up to 19, then the n becomes big, 7,000 columns, 38 rows, and we got these exact same numbers that we found with exhaustive searches previously. So at least we have some independent verification that these numbers are correct. So now they can go into Sloan's online encyclopedia, but only up to 19. So, and in summary, this is my last slide. This is the coding theory, if you like, reformulation of this structured Hadamard conjecture. You start with an odd L bigger than 1. You make up M is L minus 1 over 2. You make up your periodic autocorrelation equations. The minus 2 becomes plus 2, so this should be equal to 0. So you want to find zeros, binary zeros of this polynomial with positive integer coefficients. So Eliahu theory applies. And you reduce all the squares. This is something done, it's very commonly done in symbolic computation, right? In many different contexts. You form your matrix, lowercase n by uppercase n. You consider the binary linear code. You can prove that the dimension is 2L plus 2. That's easy to do. Any coding theorist can do that for you. The hard part is to prove that there are code words of weight n over 2, that this coefficient of or power n over 2 in the weight enumerator is not 0. You don't have to evaluate it. Even if you prove it's non-zero, you win, okay, for a specific L. And if you do this for every odd L, then you win big. That's the end of my talk, and thank you. I try to keep the time.
For the Legendre pair, from what I understood, we know that there exists a pair for every prime.
That's right.
Do we know how many pairs for each prime? Like, can we predict prime, how many pairs we can have?
Well, here is a specific prime, right? 3, 5, 7, 11. All of these are primes. And we know exactly how many we have. We know exactly that for 5, we have 50 Legendre pairs. For 7, we have 196. But not all of them come from the Legendre symbol construction, if this is what you're asking, right? The Legendre symbol construction gives you one that you can permute in a cyclic manner, if you like, and get some other ones. But not necessarily all of them, for prime orders, come from the Legendre construction. That was the question, right? Yeah. Thank you. Yeah. Well, here it is. That's the polynomial. So this is PAS. PAS is a quadratic form, the path at S. So the path for S equals 1, PAS is A1 times A2 plus A2 times A3 plus AN times A1. Yes, exactly. So this is the definition of the Legendre pair. Remember, we had M conditions that path A plus path B is equal to -2. So you bring the -2 over here. Luckily, it's positive. If it wasn't, then none of this could work, right? Yes, and this is also a square. It's a sum of squares. So if we make it 0, then that means each one of these things are individually 0. So and each one of them gives a Hadamard matrix coming from these Legendre pairs, right? Please, yes.
So, but other use of this every field variety. Is there some analogous counting of binary zeros more than one polynomial? Crunch them all into one polynomial by doing some squares.
That's a great question. Not in his paper. So in his paper, he only wants one. And that's why over here I did this sum. But someone could think, of course, when you have, let's say, 2, You can take the sum of the squares, but it's not the best way of doing it. Yeah, someone could think about extending his theory into, let's say, two multivariate instead of, let's start with two and go from there. But yeah, great question. It's not in his paper, that's for sure. And by the way, his paper is cited very few times. For some reason, I looked up his citations, and it's maybe cited since 1994. I cited it, left, right, and center. But it's for some reason, I think it went unnoticed, and it's a pity, because it can be applied in many other problems, not only this one, right? His theory has a wider applicability. Yeah.
Say anything more about the second involving lattice functions, like
Yeah, I can say that it's above my head,
yeah.
first of all. Yeah, I think they are, so they have a space of vectors with half minus ones and half plus ones. And the lattice walk is defined in that space. And if the lattice walk starts from, let's say, somewhere and ends up in the same point in the lattice, then it counts a Hadamard matrix. That's kind of the overall idea. But the technicalities, I must admit, I could never figure it out. Here, I spent some time with this paper, and in the end, I figured out what I needed to do this application, right? But in the other one, I tried again, and nada. Thank you.